And we have our warm-up problem. Here we have a sum. The sum from n equals 2 to infinity of natural log of n squared over n minus 1 times n plus 1. And there's some options. Log 2, log 4, log 8, log 9. Or, of course, maybe the sum doesn't converge, in which case we say it diverges. All right. Do we have an answer for this one? Is it B? B is a good choice, but nope, not B. Good choice, though. E? Ooh. Another excellent choice, but it's not E. So now we're down to A, C, and D.
Feeling A.
Well, one person says that they're feeling A. All right, so that's A. Log 2. All right. Now, one of the things that you quickly learn is that it's really hard to find the actual value of most series. And so the majority of time when you're asked to find the value of a sum, you know that you're looking for two things primarily: geometric or telescoping. We know this one's not geometric because geometric has a very, very precise form. It has to be something to the nth power. And there's just like, you can write it with a single n, and the n is upstairs in the exponent. And so since it's not that, it must be telescoping, which means that, okay, we need to look for cancellation. So telescoping, the idea of telescoping is you get local cancellation. So in other words, if you look at consecutive terms, somehow things cancel out. Now, when I think about telescoping, I often look at the functions involved. And because of log, we can break this apart. Log says if I have division, that becomes subtraction. I can bring exponents down. So this is the same as minus log n minus 1 plus 2 log n minus log n plus 1. Now, essentially, they look like log of n plus or minus something. And so this is the kind of thing that you look for in telescoping. It's like, oh, I have the same expression. It's just I sort of offset my inside. So here, n versus n minus 1 versus n plus 1. So I have some offsets. Now, when I say offsets, I want to say n versus n minus or n plus. That tells me how far I need to look to get cancellation. And because I have three things, it says, well, if I look at the current term, I should look at the one before and the one after. So in essence, it's really I'm looking at three pieces to be able to cancel everything off. So I want to get enough going just so I can see the cancellation. So I'm looking at a partial sum. So I'm going to have the first three terms. And I notice that the log 3 terms of the first three terms will cancel out. The log 4, starting with the second, third, and fourth term, will cancel out. The log 5 will cancel out with the next two terms, and so forth and so on. And then at the end, there's something similar that happens. Namely, if you look at the n minus 1, those cancel out. N minus 2 will cancel out, going into the dot, dot, dots. Then minus 3 cancels out, going to the dot, dot, dots. And so we say, what's left? Well, there'll be some stuff from the beginning, minus log 1 plus 2 log 2 minus log 2. And some stuff at the end, minus log n plus 2 log n minus log n plus 1. That's the idea of telescoping. Most of the stuff cancels out except a little bit at the start and a little bit at the end. And now we say, well, what hasn't canceled? Well, the log 1 is 0. 2 log 2 minus log 2 is log 2. And minus log n plus 2 log n is log n. Log n subtract log n plus 1 is log n over n plus 1. Now let n get big. As n gets big, this becomes log of 1, which is 0, so we're left with log 2. And if you've done your practice quiz for this week, you might be getting sort of a deja vu, like, this feels very familiar. And if you haven't, this is a omen of things to come. Maybe a sense of foreboding, like, oh no, something's coming. All right. Any questions on our fun warm-up problem? Well, okay. Moving on to our thought for the day. So from a well-known storyteller, sooner or later, everything old is new again, and by Stephen King. And now, when he wrote this, I'm sure he was thinking about, stories. The same stories repeat over and over, and you can get a lot of mileage out of doing the same thing. But I'm thinking of this more from a mathematical perspective, in that we can build off of old ideas. And there's this wonderful thing in mathematics is that ideas keep coming back again and again. And that's going to show up today. It's not necessary in mathematics that everything is always brand new. We build on what came before. And so it helps to say, hey, what came before? Let me make sure I have a really firm understanding of all the basics, and then let me learn how to use these ideas again and again. Well, so where are we going? What's our goal for today? We're going to be talking about the integral test. And so we're in a part of this segment of our course, this block of our course. The next roughly 4 lectures are going to be talking about how do we know if a sum converges? It's a hard question. Because, yes, telescoping and geometric sums, those are easy, but not everything is easy. So we have lots of sums that we want to understand. Hey, does this make sense? Does it converge? So that's where we're in. So we want to say, well, do we have any tools? And so one tool we're going to look at is to say, well, what if we can imagine it's a nice function, and think about, well, can I compare it to the integral? And so if you have a function, which is, and in the old exams, they say, well, what are the 3 things you need? Positive, decreasing, continuous. Actually, technically, the only thing you need is decreasing. So if your function is decreasing, then the integral will converge if and only if the sum converges. Now, why is this useful? Because we learned how to do infinite integrals. We have these tools, the improper integration. So some of these infinite integrals we can do. And that can help us answer whether or not the sums, these infinite sums, converge. And it's a sort of fun interplay. You'll notice I have some notes here, continuous and discrete. Whereas integrals, they're what we would call continuous. They work over all points on the line. Whereas the sums, they only work on the sampled whole numbers. So it's a different beast, but yet somehow we're able to connect the two together. We'll get into the error, and we'll talk about that. And but the other big thing besides the integral test, and probably the most important thing, because we're going to use it a lot, is what's called p-series. So the sum from 1 to infinity of 1 over n to a power p, so p-series refers to that p, n to the power p, will converge if and only if p is bigger than 1. So those are the ideas for today. In terms of the formula sheet, you have your p-series result in this piece right here, and this part right here is about your error bound for integral test. All right, so that's where we're going. Let's begin. And we'll start with a quick reminder of what we've done in the last lecture or so, 1.5 lectures. So some sums we can do. We can do geometric. And remember, what is geometric? Geometric refers to multiplying, and the idea is to get the next term, you multiply by r. So there's this multiplying factor. And if I want to sum a geometric series, once I know it's geometric, all I have to say is what's the first term? What's the multiplying factor? I check to make sure the multiplying factor is smaller than 1 in magnitude, and life is good. First term divided by 1 minus the multiplying factor. There's telescoping, where we get local cancellation, and that's the kind of thing that we saw in our warm-up problem. And that's almost it. Until we get to about a day or so before the exam, that's it. So most sums we can't get the explicit values for, at least not with the tools we have. So I say, okay, so what do we want? And so we say, well, I have one primary goal and a secondary goal. Primary goal, number one goal is, does this sum converge? So even if we can't know the value, we can still answer the question, yes, there is a value. So does the sum converge? It's a yes-no question. Now there's a secondary goal, and we won't do it all the time, but the secondary goal is, when it converges, can we estimate the error? Now, a better way to think about what that question is the following. If I know it converges, I want to be able to say, what does it converge close to, right? What's an estimate for what it converges to? In other words, how far do I have to go out in the sum and stop and know that I'm close to what the actual value would be? So in essence, this says, when can I stop adding if I want to be within, say, 4 digits of precision? Now, we do have one test we talked about last time, which is the nth term test. And the nth term test does not answer convergence. But it does help us a little bit, because it does say divergence can happen, or will happen, if the terms don't get small. So if the terms don't go to 0, the sum diverges. If the terms go to 0, all bets are off, no conclusion. So it's a very weak test. It doesn't help us with convergence. So that brings us to today. And so this is our goal. We've already said it, but I'll say it again. If f of x is a function, which is decreasing continuous positive, and this is how we present it. If you go to my old videos, that's probably how I present it too. If you go look at old exams, they'll often say, what are the 3 requirements for the integral test? And that's the answer, decreasing continuous positive. But ultimately, it just says, we just need it to be decreasing, and more precisely, eventually it must be decreasing. It doesn't have to be decreasing everywhere. It only has to be decreasing in the tail. When we talk about convergence, it's not the start of a sum that matters. It's the end. It's the part near infinity that matters. And so what you do at the beginning has no bearing on whether or not you'll converge. It's way down at the end, way down there at infinity. That's where the interesting things happen. So it eventually has to be decreasing. All right, then the sum converges if and only if the integral converges. All right, so why does this work? And it's a lot simpler than you think. The picture is the justification, which is to say the following. If I look at the sum, I can think of that as a Riemann sum. So in other words, I'm going to take my interval and I'm going to break it up into length 1 segments. And I say, okay, great. Now what I can do is, for any interval, I have to pick what's the height for that rectangle. Because Riemann sums is about adding up areas of rectangles. Well, I can either choose the left end, or I can choose the right end. Now, let's suppose I were to choose, say, the right endpoint. Then, because I'm decreasing, what will happen is my rectangles are underneath the curve. So, if I add up the sum of the areas of the rectangles, so think of this as f of n times 1. So, it'd be f of k plus 1 times 1. That's the area of the first rectangle. f of k plus 2 times 1, that's the area of the second rectangle, so forth and so on. All these rectangles are under the curve. So now I say, well, hey, the sum of the rectangles has to be less than or equal to the area under the curve. But now we play the game a second time, saying, well, let's not pick the right endpoints. Let's pick the left endpoints. So now the area would be f of k times 1 is the first one, f of k plus 1 times 1, f of k plus 2, and so forth. So it's the sum. Now we start at k instead of k plus 1. Sum from n equals k to infinity of f of n. Those rectangles are bigger than the integral. So the area is bigger. And the only difference between the first and the last terms is one piece at the start. And what happens at the start doesn't matter. And now the great aha says, look, if the integral is finite, the sum is finite, because the sum's below the integral. At least the important part of the sum. The important part of the sum is as you head towards infinity. So if the integral converges, the sum converges. But if the sum converges, so then this part at the end is finite, then the integral is finite. So if the integral converges, the sum must converge, because I can bound it by that integral. If the sum converges, then the integral must converge, because I can bound it by the sum. That's the idea. And it's a beautiful idea. It's a beautiful idea. All right, so what does it tell us? It tells us they both converge or diverge together. So let's try this out. Does the sum of 1 over n squared plus 1 converge? Okay, so first off, can we use the integral test here? Yay or nay? Yes, we can. Now, what are some clues? Well, we can think of this here. This we'll think of as f of n. So what would be our f of x? If f of n is 1 over n squared plus 1, f of x is 1 over x squared plus 1. We're just changing n for x. Now, is 1 over x squared plus 1 continuous? Yes. Is it positive? Yes. Is it decreasing? In other words, if I put larger values of x in, do I get a smaller number? Yes. A larger value of x downstairs makes the denominator bigger, makes the whole expression smaller. So it satisfies our requirements. Okay, so now we compare with the integral from 0 to infinity of 1 over x squared plus 1 dx. Do we know this integral, 1 over x squared plus 1? Have we ever seen it before? It's arctangent. What? How many lectures has it been since we've had a good arctangent? Too many. All right, so it's arctangent of x. Now, technically, this is an improper integral. In practice, we only break out the limits when we need them. So let's see if we need them. So arctangent of x from 0 to infinity. Now, infinity is not really a number. It's more of a concept of as things get big. What happens to arctangent as its input gets big? If you were to sketch it, what happens? Arctangent looks something like this. So as the input to arctangent gets big, what does the value do? It approaches the horizontal asymptote of pi over 2. So oftentimes we say you plug in infinity, but well, no, it's like as your x gets big, what happens? Arctangent of 0? is 0. Now, do we care about this value? No. What was the question? The question is, does the sum converge? We switched over and said, hey, we have calculus tools. The integral converges. So now we say, since the integral 1 over x squared plus 1 dx converges, then by the integral test, the sum, n equals 0 to infinity, 1 over n squared plus 1 also converges. That's a lot of words. It's one of the hard things about the upcoming exam. You have to use words. Words can be challenging. Okay, so the answer is, does it converge? Yes. Yes, it does. All right. Good. Good. Well, let's try another one. Okay. Use the integral test to determine if the following sum converges. 1 over e to the n. Well, let's not take too long. We have other things to say. So, what's the function? If this is our f of n, f of n, got ahead of myself, then what is f of x? One over e to the x, also known as e to the minus x. Okay, now does e to the minus x, is that positive, continuous, decreasing? Yes. Yes, it is. Okay, because if you graph e to the minus x, it looks like this. So here's the graph of e to the minus x. So we can apply the integral test. And we'll just go ahead and do this. Integral 0 to infinity of e to the minus x dx. Well, what is the integral of e to the minus x? This is not meant to be a trick question. I'm saving that for the next one. Negative e to the minus x. And evaluate from 0 to infinity. If you quote unquote plug in infinity, right? So in other words, as x goes to infinity, what happens to e to the minus x?
It goes to 0.
Goes to 0. So you end up with 0, subtract, plug in 0, minus 1, which is 1. So, since the integral 0 to infinity e to the minus x dx converges, then the sum 0 to infinity 1 over e to the n also converges. But I want to do just a little bit more here because I want to point something out. Do we know how to actually find this sum? 1 over e to the n? Is that something we have the technology for? There's a few people nodding their head. Okay. What's the tool to find the sum of 1 over e to the n? Or put another way, what kind of sum is it? It's geometric. So let's actually find this sum. Sum n equals 0 to infinity. And 1 over e to the n is the same as 1 over e to the n. But I'm just going to write it in a slightly different way. And 1 over e is small. So, according to our generic formula, we have to say, what's the first term? What's our multiplying factor? So what is the first term? What's the a? 1. Because when you plug in n equals 0, that would be the first term. 1 over e to the 0 is 1. What are you multiplying by? 1 over e. And if you multiply this by e over e, just so you can avoid fractions over fractions, this becomes e over e minus 1. Now here's the punchline. This number and this number are not the same. And I know this will not shock you, but when we're doing the integral, we're not finding the sum. That's an important thing to understand. We're not finding the sum. We're just determining whether or not the sum exists. So be careful. Don't think like, the integral finds the sum. It doesn't. There's error. So you have to make sure you understand that. All right. Good. Now, use the integral test to determine if this sum converges. And I don't want to dwell too long. I've already given a big hint about the integral. But I have a question. Can we use the integral test here? And why can we? Or maybe another question is like, why does Steve hesitate? Why is he saying like, Is there anything that makes you say, I don't know, Steve. I don't know. Something's a little bit different about this one.
The fact that 10 is everywhere.
The fact that what?
10 is everywhere.
People like 10s. 10s are perfect, right? As long as you're at a scale of 10, it's perfect. So what would our function be? What would our f of x be? Not big as this is not a trick question, not yet. There's our f of n. So f of x, just x over e to the x over 10, right? Everywhere you see an n, put an x. That's your function, which is x e to the minus x over 10. Now, going back to the integral test, what is it we're looking for? Positive, continuous, decreasing. This function starts by doing this. It's not decreasing, it's going up. So, does the integral test still work? Because it's not decreasing at the beginning. Someone has pointed it out. It's not the start that matters. They said eventually it will be decreasing. See, they noticed I didn't keep drawing. So what's going to happen, in fact, we can go ahead and check this out. F prime of x, we can take a derivative, and you're like, wait, I thought you wanted integration. Well, take a derivative. Because if you want to know increasing, decreasing, that comes from the derivative. So f prime of x, product rule, the derivative of the first times the second plus the first times the derivative of the second, which is e to the minus x over 10. And then derivative of minus x over 10 is minus 1/10. And now if you factor this out, this becomes e to the minus x over 10 times 1 minus x over 10. So initially, the derivative is positive. At what point will the derivative be 0? Can you see a value for x when you get the derivative of 0? At 10. So it'll continue increasing until you hit 10. And then what's going to happen to it? Well, if we go larger than 10, what happens to this part right here? This is negative. This is less than 0 for x bigger than 10. So that says it will decrease eventually. So even though taken as a whole, over the whole range from 0 to infinity, the function is not increasing, what do I care about? I don't care about the start. I care about the end. So is it at the end, is it decreasing? Answer?
Yes.
Yes. And so that's the thing we focus on. In the end, does it go downhill? All right. So since it's, so f of x is eventually decreasing.
To what extent is this going to be abused, though, on exams? Like, are we going to have to go out to like 1 million to find that it finally decreases? Or?
Oh, come on now. Would we ever be mean on exams? Do you not know your teachers? Our teachers love us. They only want the best for us.
Which means hard questions.
That sounds like tough love when you phrase it like that. All right. And, okay. That was the main point I wanted to say. And so from here, you just do the integral. Because it is eventually decreasing, you can apply the integral test. And you don't have to wait till the point where it decreases. Because, again, the start doesn't matter. It's always the end that matters. And so, very conveniently for us, we have the expression for the integral written down. I'll go ahead and write it down again. Evaluate from 0 to infinity. Now, what happens when you plug in infinity into this expression? So if I plug in infinity into x plus 10 over e to the x over 10, what happens? Upstairs you get big. Downstairs you get big. What can we do? Ah, yes. Ah, l'hôpital, mon ami. Right? So this is a time when we justifiably break out our limit. So the limit as b goes to infinity, minus 10, b plus 10, e to the b over 10. Now take care of the upper part. And then at 0, just plug in 0. And so this is taking care of the infinity part. Plug in 0, it'll be plus 100. Because minus 10 times 10 is 100. E to the 0 is 1. And then it's minus a minus 100. All right, so we're saying, oh, l'hôpital, mon ami. It's been too long. So we take the derivative. And upstairs we get minus 10. Downstairs we get 1/10 e to the b over 10. Okay, so that's l'hôpital. And where does that limit go to? Doesn't go to infinity over infinity, so that's good news for us. It goes to 10 over infinity, also known as 0. So the integral converges, and since integral converges, sum converges. I know, you're like, Steve, everything's converging. Well, we'll find something which doesn't converge. Okay. That brings us to p-series. So p-series are sum of 1 over n to the p. We know that if we look at 1 over n to the p, we can say, well, let's swap it with the function. That's 1 over x to the p. And since we only care about the interesting values for p, 1 over x to the p will be continuous, decreasing, integrable. Nice. So really, the question is, if I want to know if this sum converges, I just have to look at this integral. But we've already done the integral. We talked about this specific problem. We said, hey, this integral converges if and only if p is bigger than 1. So this goes back to something when we did improper integrals. And so we know when p-series converges. P-series will converge if and only if p is bigger than 1. Okay, so that's just a nice fact. We have it written down. It's on our formula sheet, so we can go ahead and use it. So, what can be said about some of these following series? What can be said about sum of 1 over square root of n? Do we know what that is? Does it converge or diverge? What's another way to write 1 over square root of n? One over square root of n, also known as n to the 1/2. So, what is your value for p? P is 1/2. Now, our big test. Is 1/2 bigger than 1?
No.
No. So what's our conclusion? This diverges. P series with p equals 1/2. All right, the sum of 1 over n. Now, if you came last time, this sum might sound familiar, but let's go ahead and use the idea of p series. What's the value for p here? P is 1, right? It's 1 over n to the 1. So this is p equals 1. Now, question, is 1 bigger than 1? No, it's not. So what does that tell us about this sum? Diverges. And we saw that very explicitly last time. Do you remember the name of this series? This one has a particular name. Sum of 1 over n. Do you remember? Harmonic. Yes, this is the harmonic sum. Classic example. Now, let's just make a note here. What if, I'll throw in a 1 here, 1 over n to the 1.000001. Does that sum converge or diverge? It converges. So even though these are super duper close, somehow that harmonic sum is basically right near the dividing line, converges. Okay. Sum of 1 over n squared. What can we say about this sum? What's our p-value?
2.
P equals 2. Is 2 bigger than 1?
Yes.
Yes, so what's our conclusion? It converges. So this is p series with p equals 2. Now, on a side note, this is also a very famous sum. If you look it up, this is the Basel problem. And this sum has almost coming up to nearly 300 years that it's been known. So the sum n equals 1 to infinity of 1 over n squared. Anybody know this one off the top of their head? Good guess. Pi squared over 6. And if you're wondering, are you sure you mean pi and not something else? No, it really is pi. It's pi squared over 6. And, but in general, it's hard to find these values. Now, if it's n to an even power, there is a formula for that. N to an odd power, say n cubed, we don't know a formula for that. We know the number up to hundreds of thousands of digits by now, but we don't know, is there a nice constant associated with it? Who knows? Who knows? All right, that brings us to our last part for today. Error estimates. Knowing how much of the sum do we need to look at? So we say, look, I know this sum converges, and I just want to make sure I have a good idea of what it converges to. How far do I have to go before I stop? Because I can't add to infinity. That would take infinite time. our machines are finite. So we have to say, well, when can I stop and be confident I'm within 0.01 or 0.0001 or something? So it's important if we do have this idea like I can't know the exact value, when do I know when I'm close enough? Okay. So we are going to assume that we know the sum converges, and we're going to assume that we're in a part where it's decreasing. So we know eventually, when we're doing the integral tests, we're going to be eventually decreasing. So we're in the tail, and the tail can start pretty quickly. So we have the following. If I add up to, say, the value n, and then I add the integral from n plus 1 to infinity, that's less than or equal to the sum from all the way from the start to infinity. The picture tells you the story here. So what's going on? Well, I want to say, how does this sum compare to this situation? So it's an area comparison. And, well, where did my sum stop? I stopped at n. So I'd say I need to look at f of n plus 1 plus f of n plus 2 plus f of n plus 3 and so forth. So f of n plus 1, that's the rectangle. And notice the rectangle is above the curve. So this integral, the curve, is below the sum of the rectangles. So that's why that inequality is true. On the other hand, you can say, look, this sum is below, go up to n, and then add the integral from n to infinity of f of x dx. Again, we want to say, okay, where did we stop? We stopped at n. So if I look at now rectangles going backwards, I have f of n plus 1 is the rectangle, f of n plus 2 is this next rectangle, f of n plus 3 and so forth. They're below the curve. So the integral is bigger than the rest of the sum. And these parts match. Okay. So what's the key thing? Well, this is where I stop. And now I can say, look at the sums. How do they compare? Or sorry, not the sums, the integrals. How do they compare? Well, they're very close. How much do these integrals differ by? Or how do they differ? The answer is they differ in their starts. So what you can do is if you look at this integral, subtract that integral, that's the gap between the upper and lower bound. That's the same as going from just n to n plus 1. So if I want to make sure I'm close, I just have to make sure that this integral is small. So I don't have to go add up for a long time and just say, I hope I've gone far enough. I just say, wait until I've gone far enough where I know that this integral is small. Then I can say with confidence that my error is small. So that's the idea. Now, another way to do this is just basically to say, and this is probably if you watch some of my old videos. Oh, I was so young and naive back then. My beard was much darker. But oftentimes people just say, just make this integral small. But that's more work. That's more work. Okay, so I want to show you how we can implement this. So, give expressions which differ by less than 0.01 and give upper and lower bounds for the summation n equals 1 to infinity of 1 over n squared. All right. So this is a lot to digest, but here's the idea. So we're going to sum n equals 1 to capital N of 1 over n squared plus the integral n plus 1 to infinity. of 1 over x squared dx. That's less than or equal to the sum, n equals 1 to infinity, of 1 over n squared. And that's less than or equal to the sum, n equals 1 to capital N, 1 over n squared, plus the integral n to infinity of 1 over x squared dx. So I'm just copying from the previous slide. And now the question is, how do you choose n? All right, so to choose n, the key is just to take a look at the difference. We want the integral from n to n plus 1, 1 over x squared dx, to be small. What is the integral of 1 over x squared? Also known as x to the negative 2. Well, think integral, not derivative. So x to the negative 2, you add negative 2 plus 1, you get negative 1, and then so it'll be negative 1 over x. Evaluate this from n to n plus 1. This becomes minus 1 over n plus 1, minus minus plus 1 over n. And if you do a little bit of work adding these together, you get minus n times n plus 1, plus n plus 1, n times n plus 1, which is 1 over n times n plus 1. Now, this is how far apart the upper and lower bounds are. Our goal is to make that small. How small? This small. So we say, all right, we want that to be less than 0.01. Can anybody see a number n where that's true? In fact, can you see the first n where that's true? Ah, the anticipation. I'll give you a hint. It's not a big number. You may have seen it before. 10. So n equals 10. So what does this say? If you add up 1 over 1 squared up to plus 1 over 10 squared, plus you do this integral, and now this integral will turn out to be 1 over 11. That's less than or equal to the sum of 1 over n squared from 1 to infinity, and that's less than or equal to 1 over 1 squared plus up to 1 over 10 squared plus 1 over 10. And just for reference, because I went through and computed this, 1.6406, 1.6497, and the actual value, 1.6449. So that's an idea. All right, that's it for today.